Welcome back to I guess, what is the penultimate lecture of the semester. We are picking up our discussion on VAEs. We're diving deep into what variational inference is and what something called evidence-based lower bound optimization is, which is what ELBO stands for. Let's take a recap from last time, and I want to preface this particular lecture by saying I think this is one of the mathiest lectures in the entire semester. This is not by design, except it is a little bit by design in the sense that there's a particular topic that we want to teach you, and if we break it up across multiple lectures, it just gets a bit confusing and heavy. So it's sort of densely packed into this lecture. You'll indulge us into that packing. One thing I can tell you is that I personally find this topic just sort of fascinating, and if you've seen the movie Matrix, and I am obviously dating myself at this point, there's a moment where skills are downloaded into the protagonist's brain. You will feel a little bit like that. You'll wake up and say, okay, I understand variational inference. So hopefully that's the goal today. All right, so let's take a look at recap from last time. We are building up towards VAEs. And in order to understand that, we sort of gave you this argument that so far everything that we've been building in terms of generative models has been fully observed generative models. So if X is our random variable, we've been building models directly in terms of the components of X. And the argument we made is that there are sometimes benefits that can come if you start modeling latent variables or variables that are not observed in your data set. So even though your data set contains only X, we can construct distributions over X and Z, some hidden variables, where P of X given Z is somehow simpler. And the problem that it comes with is that it results in this marginalization problem over Z when you have to compute likelihood of X. And this can be often difficult. We sort of gave you one example of a latent variable model, which was a Gaussian mixture model. We sort of worked through the math of Gaussian mixture models. We said the latent variable in Gaussian mixture models is categorical, just tells you which Gaussian we are sampling from. And then P of X given Z is a univariate or a multivariate unimodal Gaussian. So P of X given Z is a simple object, but P of X comma Z is a mixture of Gaussians, therefore more sophisticated object. And we ran through a couple of scenarios of operations that you can ask for. You can ask for marginalization. You can ask for posterior inference, as this operation is called. If I bring you a data point, can you tell me what Gaussian it came from? And other sort of queries that you can ask from such models. And these are the same kind of queries that we'll ask from VAEs. We told you that VAEs are really composed of four somewhat independent ideas: the idea of autoencoders, the idea of variational approximation, and two other ideas. We covered autoencoders. We will dive deep into variational approximation today, and we'll also see amortized inference neural networks. We will not see reparameterization trick today. Okay. For autoencoders, refresher, we told you that it's just a compression problem. You go from RD to RK back to RD. You reconstruct your input. Therefore, it doesn't use any labels. And you train this neural network to do that. We told you that the problem we're trying to solve is that this is a deterministic neural network. Therefore, the intermediate representations Z are not random variables. They are deterministic functions of X. Therefore, you cannot ask this question, what is P of Z given X? I mean, you can ask it, but it's a delta distribution. It's a trivial distribution. It does not have any uncertainty. You cannot sample from it. You cannot see what are other possible things. And similarly for X hat, the reconstruction from Z is also a deterministic operation. You cannot ask this question. Is there any uncertainty in reconstructing X from Z? And that is what VAs provide or build towards. Okay, so VAs will take X and give you a probability of Z given X, and will take Z and give you a X hat given Z. So they have a probabilistic encoder and a probabilistic decoder. And as you can probably imagine in the way we're building up to things, since this is a deep learning class, both of these things will be neural networks. The probabilistic encoder and the probabilistic decoder will both be neural networks with some parameters phi and theta that we will learn. Okay, so let's pick it up on variational inference. That's the plan for today. And then we'll get to evidence-based lower bound, and then we'll put it all together. So last time we had just started introducing the idea of variational inference. Again, variational inference is an idea that is independent of variational autoencoders. Variational autoencoders use this broader idea, but you will come across this idea in many other contexts. And that's why we're sort of introducing it somewhat independently. The key idea of variational inference is a simple idea, which is reality can be complex. There can be some distribution P of Z that is something fairly complicated. We want to approximate it with something simple, maybe you were going to use P of Z to construct some expectation of some function. You were going to use P of Z in some way. What we're going to do is we're going to do a replacement. We're going to replace P of Z by some simple distribution Q of Z to construct this expectation. Now all we have to do is find a good approximation to P to introduce into this downstream computation. Okay, so last time we had sort of drawn this intuition of variational inference as you have a class of distributions Q, not just a single distribution Q. And what we're going to do is minimize the KL divergence between Q and P. And what we had said is that, look, in homework 0, you showed that KL divergence is a measure, but it's not a distance, it's not symmetric. There are two ways of writing KL, right? We could write KL P to Q, or we could write KL Q to P. And they are going to lead to fairly different outcomes. And if we just sort of write it out, KL of P to Q is going to be sum of Z PZ log P over Z by Q over Z. And KL of Q to P will be sum over Z QZ log QZ by PZ. Now, if we just stare at these two expressions, we can see that this part of the expression, the PZ by QZ expressions, are fairly similar in the two. There's just an inverse relationship. You should treat PZ by QZ as a sense of error. How far are these two? How different are these two distributions? If I bring you a data point Z and your original true distribution P of Z says this is very likely, and your Q of Z says it is not very likely, then this error signal is high. This is a bad situation to be in because you should be close to P in that sense. When this ratio is close to 1, that's when your error is low. Q and P are agreeing everywhere on all data points, all parts of Z, right? So, and whether you measure Q over Z or P over Q or Q over P, it doesn't really matter as long as they both have full support, meaning that you're never dividing by 0. As long as that's not happening, this ratio, whether you do P over Q, Q over P, doesn't really matter. The differences come here. This is a log error and an expected value of that log error, or a weighted average. And these terms are specifying the support. How are we valuing, how are we weighing these errors? And in one case, in KL-P2Q, we are weighing the error by the right thing, by the distribution that actually tells us how our data is going to be sampled. And in Q2P, we are weighing the error by the wrong quantity. We are weighing it by a measure that we control that is not actually the data generating distribution. And this is what leads to problems when you optimize them. Let me see, I'll come back to this. So here is a particular example that illustrates that problem. Let's say our P, which is the true distribution, the more complex distribution, is a mixture of two Gaussians, right? So the blue curve is P right here. So this is P of Z. This is a two-dimensional distribution. This is Z1, this is Z2. The blue thing is P of Z, and the red thing is Q of Z, which is a single Gaussian. We want to approximate a mixture of two Gaussians with a single Gaussian. You can see the level sets. You can see that the Q distribution is, the P distribution has two modes. There is mode number 1, and there is mode number 2. There are two sort of peaks in the thing. When you minimize KL P2Q, the error signal is averaged by P of Z, meaning that you have to have support where P has support. When you minimize KL Q to P, Q decides, notice that Q is the optimization variable. So what Q can say is that I will focus on mode number 1 or mode number 2. These are two optimization runs of this minimization process. These are two equivalent minimas depending on the optimization. And what Q decides is anything outside of where I place support does not exist. Therefore, error there does not matter. And so that's why, because you've handed the weighing or the support into your optimization variable, it latches on to one of the modes, explains it well, meaning that the error ratios are low, and everything else outside here where the error is high, because in these regions, for mode number 2, P is high, but Q is very low. It just doesn't matter because Q is also the quantity that is doing the support estimation. So at bad error locations, if your Q is 0, it won't show up in your KL computation. So in KL P to Q, the true distribution defines the support. This is the correct direction. It will typically be intractable. In KL Q to P, the approximate distribution defines support. It tends to give overconfident results. It will be tractable, but it's the sort of wrong direction. Okay. Any questions on this part before we move on to an application of this idea? So this is broadly what is variational approximation, the idea of approximating distributions by a family of simpler distributions. What we will do today is then we will transition from this idea of variational inference and show how it applies to VAEs and what an evidence-based lower bound is. So let's go from here. Let's start putting things together towards VAEs. Remember that the key problem in VAEs that we're going to solve, that is also a general learning problem with missing data. Anytime you want to do unsupervised learning in probabilistic models, or anytime you have a probabilistic model with variables that your data set does not contain, you're going to run into this problem, which is that you're going to write down the likelihood of your data. And the likelihood for us is what we are calling this log likelihood LL function, which is the log probability of all your data points. So you have a data set, your data set contains xi, I going 1 through n, and so we are summing over all the log probabilities of these data points. And because we have a joint distribution, our model has a joint distribution P of x given z, we have to marginalize across that joint distribution that is sitting inside the log. By the way, for most of these calculations, I will ignore this summation sitting outside on x. It tends to not be the bottleneck. Yes, there is that summation in all the expressions. There's just this one extra summation, but that doesn't really cause any problems. So that's the coming back to this. That's the problem that we are dealing with. That there is a log likelihood function in a model that contains variables that are not annotated in your data set. Therefore, you end up with this LogSum probability thing. And by the way, I can sort of write this as P of xi given z comma theta, P of z. Actually, let me do a different factorization. Let me say I can write this as P of xi given theta times P of z given xi comma theta, right? That's just the chain rule applied to this thing. Now that I have a sum over z, you can see that this is an expected value of a certain quantity. So I can write this as expected value of P of xi given theta under the distribution P of z given xi comma theta. And we have a log of that. So this is what log likelihood means in these hidden models. And this is what I was saying, that there is a complex distribution. This is going to be the complex distribution, P of z given xi. This is a quantity, f of something that we want an expectation under. And we want this complex distribution we will replace with a simple distribution. So we will replace P of z given xi with a simple distribution. Okay, coming back to where we are, we have this log sum probability sitting, so the sum of something sitting inside the log, and that's a problem that we want to solve. The key tool or the mathematical sort of trick that we will use is something known as Jenkins Inequality. This is something that some of you used in a proof that we had asked you to do in, I think, homework 2, but I'm blanking out on exactly which homework. Jenkins Inequality is a fairly simple, and I'll explain it to you what Jenkins Inequality is. In its full generality, it says log sum P of z, Pz times Gz, is lower bounded by sum of P of log z. Now that seems unnecessarily complex and seems to have a lot of moving parts to it. But if you really want to understand like Jenkins Inequality at the heart of it, just think of it as concavity and a generalization of concavity. I think of Jenkins Inequality in this way, that I think of the log function, right? It's just a simple concave function to visualize in my head. And we know that concave functions have this property that I can sort of have lambda 1 z1 plus lambda 2 z2. This is a point along the way. This is f of z1. This is f of z2. So this is a concave function, f. And you know that we know that we can, where, oh, by the way, lambda 1, lambda 2 are both greater than or equal to 0, and lambda 1 plus lambda 2 is equal to 1. That's the standard thing. So we know that the definition of concavity is that f of lambda 1 z1 plus lambda 2 z2 is greater than or equal to lambda 1 f of z1 plus lambda 2 f of z2, right? This is just definition of concavity of f, right? If f is concave, then this is true, right? And by the way, I can write this in a sort of compact way by saying this is f of summation lambda I z I going 1 through 2, is greater than or equal to summation lambda I f of zi, I going 1 through 2. This is exactly the same expression. And Jensen's inequality just says take this 2 and replace it by k. That's it. That's Jensen's inequality. That instead of 2, we have sum over some k variables. So there's not just a single lambda 1, lambda 2. There's like lambda 1, lambda 2 till lambda k. There's some k possible settings, and we can get that. That's literally Jensen's inequality. And then you realize that, you know, if it's lambda 1 all the way to lambda k, this is basically a point on the k minus 1 dimensional simplex. And so this is a distribution that I can view it as. And so I can write it as f of expectation of z greater than or equal to expected value of f of z under this distribution specified by the lambdas, right? And oh, by the way, I can replace z by some other function g of z, and I can get exactly what Jensen is in its full form. F of expected value of gz is greater than expected value of f of gz. And that's what Jensen is saying for a particular setting of f. F is log, and you get exactly what Jensen's is. So I like thinking of it this way because it's like from first principles, it's literally concavity of log generalized from 2 to k, and then you exactly get what Jensen's saying. Okay, so that's all good. That's what Jensen's is. But we said, you know, this is the trick that we're going to apply to solve our problem. So I'll have the trick up on the screen. And the problem that we're trying to solve is that we have log likelihood, which is log p of xi given theta. That's the object that we want to deal with. Notice I've dropped a summation over I because that's not essential. Oops, let's not. Yeah, and this is log sum over z p of xi comma z given theta. So this is the object that we're trying to simplify. I'm already telling you that we will simplify it using Jensen's. So now this becomes a little bit of a game of pattern matching, right? Like I know how I want to solve this. I know what trick I need to use. So I'm already seeing a g of z. I just don't see a marginal distribution p in terms of z, right? So I don't see a distribution over z. I see a log. I see a sum. Everything else is good. I just don't see a distribution. And so the answer here is, when in doubt, when you don't see a distribution, just add a distribution. So we just will multiply and divide by some new distribution q. It's a new variable that we will introduce into our optimization problem solely for the purpose of making it look like Jensen's. You know, Jensen's has a marginal distribution over z, so let's just multiply and divide, and we'll assume that q has full support, so we're never dividing by 0, but then this is just 1 over 1, right? Like, so this is fine. And that's it. That's the entire trick. And now you notice that this is term 1 and this is term 2. And we can now write this in a slightly simpler, we can apply Jensen's. So we can say this is greater than or equal to, because that's what Jensen's is saying. This is greater than or equal to summation over z qi of z log p of xi comma z given theta divided by qi of z. So that's it. This object right here is called this object right here is sometimes called free energy. In the literature, we will refer to it as f of theta comma qi. This is an object that depends both on theta, the optimization variable that we want to optimize over. We want to learn the parameters, and we have introduced a new optimization variable q. This is called free energy because it was first, used and invented. This approach was used and invented in the context of modeling physical systems and energy of physical systems, and that's sort of why in that context it literally meant energy in the context of physics. Now it is not used that way, but we sort of still use the term free energy. And the fact that this is providing us a lower bound, the fact that log likelihood of theta is lower bounded by f of theta comma qi. We've introduced a new object in terms of qi. This is known as a variational lower bound, or evidence-based lower bound. And evidence-based lower bound optimization is what is the term ELBO that you will see if you ever read any of papers in this literature, like the VAE paper. And basically now that we've come up with a lower bound on log likelihood, instead of maximizing log likelihood over just theta, we will maximize log f of theta comma qi over these two objects. So this is the optimization problem that we actually end up solving. And this is a simpler problem because we've introduced a new variable and because Q is a simpler sort of distribution. So this is the application of Jensen's inequality that leads to the variational lower bound. So this is what a variational lower bound is. Okay, we're getting there. Hang in there. I know this is getting a bit mathy, but just sort of stepping back, we're building towards VAEs. This is a general concept of variational lower bound. This is going to be useful at a bunch of places. We're almost there. Well, maybe not almost. We're half an hour away, but hang in there. So this is log likelihood, free energy. This is the expression that we just derived, Q log P of xi comma z divided by Q of z. Now, what you will see in the literature is that there are two ways of factorizing this joint distribution, P of xi given z. I can either factorize it as P of xi given z comma theta times P of z given theta, or I can factorize it as P of z given xi comma theta times P of xi given theta. These are both equivalent factorization. There is a joint distribution x and z. You can factorize it on x given z, then on z given x. They're both valid. One of them is used commonly in the VAE objective function. This direction shows up here, and the other one is used commonly in the Gaussian mixture model objective function. So this is kind of what ties everything together in what we've been teaching you, that Gaussian mixture models and VAEs will end up looking very different in their modeling choices and in their objective functions, but it really is maximizing the exact same variational lower bound, which is you want to maximize log likelihood. You cannot. It is difficult. You establish a free energy function in terms of an auxiliary distribution Q on every data point, and you factorize it one way, you get the Gaussian mixture model objective. You factorize it another way, you get the VAE objective. Okay, and so those are the two sort of derivations coming next. We'll see what happens when you factorize it this way. We'll see what happens when you factorize it that way, and that'll be it. That's the extent of math coming. So let's take a look at what those two directions are. Okay, take a deep breath, hang in there. This will be over soon. Okay, so log likelihood, lower bound, same thing from the last slide, Q log P of x comma z divided by Q of z. And we said we will factorize this as P of xi given theta times P of z given xi comma theta. This is the direction that is used in Gaussian mixture model objective. It's sort of simpler, builds intuition. We'll take a look at it. Okay, so I've factorized this. What I'm going to do is I'm going to pick one of these terms, the first one, the p of x given theta term, and I'm going to, this is log of a times b by c, and I'm going to pull that first term out into a separate term and leave the other two separate. And by that, what I mean is I will say that this is, oh, and I'm ignoring this summation over I, that's just repeated, so it doesn't, for simplicity, I'll sort of ignore it. So I'll say this is sum over z qi of z log of p xi given theta. So I've pulled one term out, and in a second term, qi of z log of p of z given xi comma theta divided by qi of z. Okay, so that's just log log ab equals log a plus log b. That's the only factorization. But it's not a and b, it's log ab by c, and so log a plus log b by c. Like that's the, I've sort of written that separately. So the first thing that you can notice is that the reason why I've done that is, by the way, there's a summation over z. This term doesn't actually depend on z. So this is really a summation of a distribution over its support. So this just vanishes. This is just sum to 1. And that just leaves log p of x given theta, which is p of xi given theta, which by the way is log likelihood. That's what we've been working with. So now what I want people to tell me is what this second term looks like or reminds you. And this is really the moment of truth where I find out if I've lost my audience or if they're still tracking along. Can you tell me in the chat what that second term looks like to you? I will give you a hint. There are not too many sort of objects that look like q times log p over q kl. It's actually negative kl because q is sitting in the denominator on the right. It's negative kl of qi of z with respect to p of z given xi comma theta. It is kl. And this is what we've been saying all along about inference. And so now let me just say, this is equal to f of theta comma qi. That's what we started with. This is pre-energy equals, we derived this. And so now we have this very weird thing that's happening. We knew this expression says, this expression says log likelihood is lower bounded by the free energy f. Free energy is equal to, oh, by the way, this is log likelihood, right? We just derived that this is log likelihood again. So free energy of theta comma qi is equal to log likelihood of theta minus this scale. And so, I can write KL again. And so this makes sense. We know that it's lower bounded, and we know what it's lower bounded by. Yes, f is less than, KL is always positive. So yes, f is obviously less than log likelihood, but we know exactly how much it is less. It is less than this quantity, which is the KL. How far is my simple distribution Q that you introduced from this P of Z given Xi? P of Z given Xi is the complex object. Q is the simple object, and the farther it is, the worse your approximation. And so this is a very nice sort of closure of what we've been going for. When you maximize f of theta comma qi, the free energy, when you maximize this, you are trying to maximize log likelihood, and simultaneously you're trying to minimize this KL, right, because of the negative sign. So if, by the way, you can drive the KL down to 0, which is what someone asked the question for approximating two Gaussians with two Gaussians, then maximizing free energy is the same as maximizing log likelihood. KL can never be negative. It can never go negative. So how far can you drive it down to low? You can drive it down to 0. And so you've gotten a very precise handle on how bad your approximation is, how bad your lower bound is. It is as bad as the lowest you can drive down the KL to. And now you see why we were approximating 2 Gaussians with 1 Gaussian. Because if you choose a simple model class, a Q that is too complex, then you'll be able to drive the scale down to 0, but you won't be able to do this optimization well. And so that's the sort of relationship that is very nice to know here. Okay, and so yeah, we'll sort of relate this to. By the way, notice that this is KL Q to P, not KL P to Q, so it's the wrong direction. But this direction is tractable. That's what we arrived here by solving this tractable lower bound. Okay. And this factorization is used in Gaussian mixture models. In Gaussian mixture models, we define this free energy function, and there is an algorithm called expectation maximization that corresponds to coordinate ascent on F. So we maximize theta and QIs of F in an alternating manner. In an E step, we fix thetas, that is our current estimates of the Gaussian, and we maximize F over Q. And in another step, we fix Q and we maximize F over theta. Yeah, I won't go into a lot of the math of this, but I will show visually what that looks like. Visually, what that looks like is, this is the start of, this is a data set. Every circle here is a point. At the start of the optimization, notice here that your parameters theta recall they are the prior probabilities. So there's 3 Gaussians here, red, green, and blue, pi 1, pi 2, pi 3. There are the mean parameters mu1, mu2, mu3, and the covariance matrices sigma 1, sigma 2, sigma 3. Those are the parameters that we need to estimate. We will define a Qi of Z, which is for every data point I. I goes from 1 through n. For each of these data points, this is a distribution over 3 values, over k, which is 3. So initially, we will maybe initialize it like 0.3, 0.3, 0.3. This Q distribution is being shown in these pie charts at each data point. So this is how we've initialized the 3 Gaussians, the red, green, and blue. They have their mean values and their covariance matrices. Initially, depending on where the data points are, whether they are overlapped or under 1 Gaussian or not, we get this distribution. This data point believes it's nearly well explained by the red Gaussian. This data point right here is equally split 0.3, 0.3, 0.3, and this one is most explained by the green Gaussian. We alternatively hold theta constant, meaning that for these Gaussians, what we update Q, which is what these values are, then we hold Q constant, and then we learn thetas, which is we learn what are the Gaussians if I know that this data point is 1/3 green or things like that, so I can estimate the means and cluster centers. And this is what that algorithm looks like. The Gaussians centers are getting estimated. So I'm running the algorithm backwards now, and this is me running the algorithm forwards. And after the 20th iteration of going back and forth, we have now converged onto this setting where there is one particular Gaussian here, one particular Gaussian here, one particular Gaussian here, where the means and the covariances of those Gaussians have been chosen such that they well explain these set of data points. And the Qi of Z for these points is nearly RGB, so 0, 1, 0. So it's the G column or the green column is nearly 1. For these, it's in the third one, and these ones. Does that make sense? So let's take a look back to our original objective and look at, I said there were two ways of factorizing this. We'll look at the other direction of factorizing it as well. Taking a step back, we have log likelihood. We have some model, P of x, comma z. Z is not observed in the data set. We have log likelihood with respect to x, log likelihood of theta with respect to x. We derived free energy, which is a lower bound on that. In order to write down that free energy, we introduced these new variables Q. We wrote down this objective. Now what we're going to do is we're going to factorize this in the opposite way that we did for Gaussian mixture models. And that's the factorization that VAEs will use. And this factorization is P of xi given z comma theta and P of z given theta. This is just, we had done z given x, now we're doing x given z, just the opposite way of doing that factorization. I'll still do the same trick. I will pull one of these terms out separately, and I will pull two other terms separately. So this f we can write as equal to summation z qi of z log p of xi given z comma theta plus summation z qi of z log p of z given theta divided by qi of z. Okay, and I will ask similar questions. These are the two terms that we get. Notice we cannot pull that same trick as last time. This is qi of z, and this term now clearly depends on z because z appears in the thing, so we cannot just cancel that out. But we can write this as expected value under qi of z of this quantity log p of xi given z comma theta. So this is term number one, and the second term, does that remind people of something? And this is again one of those hints. There are not too many things to remind you of. What is the second term? What can we succinctly say it as? This is negative KL, first of all, of qi of z with respect to p of z given, sorry, not x, z given theta. Z given theta, yep. So it is a KL term. It is still in the wrong direction. We have not. It is not the case that VAEs optimize the right direction either. But this right here is the VAE objective function. This is the objective function that VAEs maximize in order to fit a model. And so just to understand this objective function, the first term here is saying, is sort of like a explain the data term, because you want to maximize this lower bound. You want both of these terms to be high. So the first term being high means that you want to pick a q and you want to pick a theta such that the x that is actually observed receives high log probabilities. So you want a q distribution that and a theta parameter that makes your x that is actually observed very likely. Because this is a maximization problem, you want KL to be low. And this is a prior distribution. Z now does not have any dependence on x, right? This is not P of Z given x. P of Z given x is the posterior inference problem. This is just P of Z given theta, meaning a priori, before seeing any data point, what do we believe about the hidden random variable Z? If z is continuous, we could just make this Gaussian, the standard Gaussian. So this is a sort of a fixed term, and this is therefore a regularizer, which is B simple. You cannot pick. So notice that nowhere in this expression is x appearing. There's just no x in this term, which is why it looks like a regularizer, right? Most regularizers are not data dependent. So this is just saying that whatever auxiliary or pre-variable q that you introduce should not be too complex, where complexity is measured by distance to the prior distribution p of z given theta, which we will typically hand set to a standard unit Gaussian, if you will. So this is the objective function that VAEs maximize. Explaining the data with some regularizer, you will see them written down this way, but know that they are maximizing the free energy, which is the lower bound to the log likelihood, which is what's related to all this other stuff that we told you about. Okay, so that is basically it. We are at this point done with explaining to you what an autoencoder is, and done with explaining to you what variational approximation is, and what variational lower bound is, what an evidence-based lower bound optimization is. And now we can start to put things together. Now we can, there'll finally be a moment of, oh, why did we learn about this and all of that? Because we can, try to build towards those probabilistic encoders and probabilistic decoders. There is just one more idea, which is a very short idea, not very mathy, that we need to introduce, which is the idea of amortized inference neural networks. And this is the final sort of idea that was used or proposed in the VAE paper from a few years ago, which is this idea that, to summarize this idea, the idea says, let's shove a neural network into a Bayesian inference problem. Which basically says that you realize in Gaussian mixture models, we were doing this thing of Qi of z, which we were storing as 0.3, 0.3, 0.3, and we were just initially, we were storing 3 numbers for every data point, and then we were learning or updating these numbers. Those pie charts I was showing a few slides ago. This is a parameterization that says for every data point I, you have to store 3 numbers. And an amortized inference neural network says, look, why must I store these distributions as separately for each data point? Why don't I just feed in X and ask my neural network to produce Q of Z for this data point? So instead of this parameterization, it's a parameterization that says, I'm going to take a neural network. Notice that this was for the ith data point, right? So I will just feed my neural network xi, and I will ask it to produce q, and this neural network has some parameters phi, and I will ask it to produce q phi of z given xi. Sorry, not theta. I'm sort of getting into muscle memory at this point. Right. So I will this idea of a posterior inference that given a data point, what Gaussian must it have come from, instead of storing independent distributions and then doing using Bayes rule to compute these things, why don't I just have a neural network that predicts this? So if z is discrete, then I will just have a softmax layer at the end. If z discrete, and notice that this is called amortized because for all data points I, there is a single neural network and a single setting of parameters, so the parameters are shared. That's the amortization part. This is an inference neural network because it is solving this inference z given xi. That's what we called inference in this context, if you remember from earlier in the lecture. If z is continuous, if z continuous, that is z lives in some r to the d, then it's the same thing. All you do is you basically assume that z given xi is, let's say, normal with some mean parameters z comma xi and covariance parameters z given xi. And what I'm going to do is I'm going to have a neural network that takes in xi as input, and it produces two quantities as outputs, two vectors. Maybe there's some two fully connected layers at the end. One of them produces my mu of z given xi, and the other one produces the covariance matrix strung up z given xi. And that's it. That's like, I'm going to treat these two parameters as, parameters of a Gaussian distribution. And this is a very weird way of thinking about it. Like, everything that we've told you so far has said that, the intermediate variables in neural networks are variables in a computational flow graph. They're deterministic variables. And here, the idea of amortized neural networks, they come along and they say, yeah, the intermediate variables can be deterministic, but I can just treat certain outcomes as parameters of a distribution, which makes a random variable, which specifies a random variable. And that's how we get probabilistic encoders and probabilistic decoders. We have a neural network that takes in x and has some parameters phi, and it just gives us the mean parameter and the covariance parameter for the normal of z given x, and we do the same thing for x hat given z. And this is a fairly weird way of thinking about it. It means that, imagine this sort of a neural network, which is this image strung up into a long vector. And if it was just a classical autoencoder, we would go forward, compress it to two numbers, let's say, and then decompress back the same pixel image. That would be an autoencoder. But in a variational autoencoder, those two numbers, we just interpret them as mu and sigma. We just say, well, whatever the activation is at this neuron, I'm going to treat that as a mu parameter, which is a mean. Whatever the activation is at this neuron, I'm going to treat that as a covariance. And I just have to make sure that it's the output of a ReLU, so it can't be negative. Covariances are not negative. And these two, because they are the mean so phi here consists of this mu and sigma, not a set. The list mu and sigma. So because these two parameters are specified, I can obviously sample z, right? Because if you tell me the mean and the covariance, that's the distribution. Notice that the z variable isn't even showing up here. There is no random variable z in the neural network. The neural network is just producing the means and the covariances, but I can sample now, and I can do the same thing at the output state as well. I can treat half of these as the means and the other half as the covariances or the appropriate sizes, and then I get these two distributions. So that is an amortized inference neural network, and we can now start to put everything together. Variational autoencoders optimize the variational lower bound, the log likelihood lower bound. This is exactly the log likelihood lower bound, log p x given z, KL divergence of q to p. That's exactly what we've been saying this entire time. It's a variational lower bound to the likelihood, to the log likelihood. And what they look like is that you start with an input x, just like you would with autoencoders. You have an encoder network, which is a neural network that produces not z, but mean parameter for z and the covariance parameter for z. And we are going to use these mean and covariance parameters in our estimation of the KL divergence term. Because if you tell me that z is Gaussian and you tell me its parameters, I can estimate the KL divergence in closed form, or if it is Gaussian, or I can also sample it for one data point. Given that sampling of z, so if you tell me the mean and the covariance parameter, then I can sample one Gaussian with that mean and covariance. And I can, for that setting of z, pass it to a decoder neural network. This is a decoder neural network that takes in the sample and produces the mean and the covariance estimate for X given Z. So this is the X reconstruction, X hat given Z. And with these mean and covariance estimates, I can sample from X given Z because this is normal as well, and I can compute log P of X given Z from that. Okay, so that's how everything fits together. This part right here is the variational lower bound. This part right here is an encoder neural network. This part right here is a decoder neural network. Those are the connections to autoencoders. And the fact that the encoder neural network is a amortized inference neural network. We produce means and covariances, not actually Z's. We just sample Z from that mean and covariance. That's what ties the previous set of slides together. Okay, so we put everything together. X through an encoder network, estimate mean and covariance parameters, sample a Z, use that sampled Z to feed into a decoder network, estimate mean and covariance matrices of X given Z, sample a reconstruction, use both these samples to estimate objective function, which is a lower bound to log likelihood, compute gradient of this through backprop, just like we have been doing through the rest of the semester, compute the gradient of this with respect to phi, compute the gradient of this with respect to theta, those are your two setting of parameters, and take a step in the direction of the gradient or the negative gradient. And now what we can do is we have finally probabilistic encoders or probabilistic decoders. We can generate data. So for example, this is a figure from the original VAE paper, which showed that you can take two spaces. There is the Z1 space, Z dimension, and the Z1 dimension, and the Z2 dimension. And you can see, you can, vary Z1 and Z2 dimension, and you can sample multiple X's for those dimensions. You can, of course, also sample Z's and see so instead of enumerating Z's, you can also sample Z's and see what sort of X's you get. And we notice that, the Z space seems to be learning something about the slant of the digit versus its identity, and the sort of, straight lineness to curviness in another sort of dimension. So very Z1, very Z2, this is the data manifold for the two-dimensional Z. And we can also do this on images of faces. And so one of the dimensions seem to correspond to head pose, and the other dimension seem to correspond to degree of smile. Notice these are qualitative assessments provided by humans and individuals looking at this data. There is no automatic extraction of semantics. All we know is we have learned some latent dimensions Z with some mean and covariance estimates that we can use to compute a probabilistic model. And this is a good feature representation that can be computed using Q5 of Z given X. So that's sort of one benefit of doing this whole thing. Overall, VAEs are, they haven't quite produced the highest quality images as they are, coming back. They have certain strengths and weaknesses. The strengths are that they are a explicit density model, meaning that you can do comparisons really easily. You can come to, you can have a held out data set and you can ask for log probabilities of that held out data set. But if you want, these are the quality of images, they improved a little bit in follow-up papers, but the VAEs never really generated the kinds of high quality images that GANs did. And for that, we can wait till the next lecture. So overall, that's all of variational autoencoders. They are a principled approach to generative models. They allow inference of Q of Z given X. This can also be useful for feature representation. The cons are that they maximize the lower bound on likelihood, and the cons also is that they produce samples that are lower quality than state-of-the-art GANs. And there's a rich active literature in VAEs and understanding VAEs. I think everything that we've told you today about a variational approximation, variational lower bound, amortized inference neural networks, I think those are more general ideas than just VAEs, and I hope you'll find them broadly useful in your research. I mean, you may find that you're not really doing image generation, you're not doing you're not doing anything to do with autoencoding, but maybe you are creating a probabilistic model which has some hidden variable sometimes. Like maybe you have data coming in from sensors, and maybe there are periods where that sensor goes down, and so there are unobserved variables that you want to marginalize over, and you need a probabilistic interpretation of those variables because you want to sample or model uncertainty. And so these are the sort of techniques that you would go at and look at. So we taught you everything for the simplest possible model, right? It was just a simple model of x comma z where x was observed and z was hidden. But these ideas apply to multivariate models where x can be, x, y, z, whatever. There can be multiple variables that you're modeling simultaneously. Okay. So we'll stop there. We will not introduce any new content, but I'm happy to take questions at this point.